Hello everyone. Today's lecture is on valve performance relationship. In this lecture, we will understand the mathematical expression for the valve flow profile. Let us revisit our production system. That's where we had established the relationship for the IPR, the bottom part, where we understand how the flow through reservoir is happening and the gas is reaching to valve bore condition, and the bottom of the valve bore where the pressure is PWF. This is very much required because it tells us the potential of gas reservoir, how much gas is available underneath or in the reservoir domain, how much maximum production can be achieved. In today's discussion, we will extend our knowledge for valve bore section, that is from PWF to surface, that we say PHF. So, PWF is bottom hole pressure at valve bore and PHF is pressure at well head. Because of the pressure difference, again the flow will happen, and the relationship between this pressure gradient or the pressure drawdown with flow rate Q, rate with which the flow can be achieved from this valve bore, and the dimension of the valve bore, like the diameter, internal diameter of this valve bore, is a part of today's discussion. This is very important because WPR allow us to calculate the achievable gas production rate. We will see, before we are going to understand the mathematical relationship, how this pressure PWF and PHF are related to production rate Q and the other parameters of the fluid and the geometry of the valve bore. Let us understand some of the basic part of WPR, that comes under valve bore diluvibility. It is important for gas engineer because it allow us designing gas well equipment. If well understanding of the WPR relationship is achieved, the designing of gas well equipment will be much easier. Not only the designing part, it also help us in optimizing the well production condition. At what condition the well should be producing, what should be the head PHF, what should be the bottom PWF pressure, and the diameter of the tube should be chosen, and at what rate the production should be accomplished, that is matching the surface facilities requirement in terms of the capacity of the gas and the pressure the surface facilities can handle effectively. Knowing bottom hole pressure at a given well head pressure and flow rate. So, once we develop the WPR relationship, you will see at the end of this class, in terms of some example we will discuss, when we could establish this relationship, we can calculate bottom hole pressure, that is very much required in IPR relationship, that can be calculated with WPR once we know what is the well head pressure and at what rate the well is producing, or vice versa. If two are known, third one can be calculated. WPR of course depends on the geometry of the producing string. So, the production is happening through the tube, through the casing or through the annulus, depend on what size of that tubing is, how long the production string is, the WPR depend on that, as well as the properties of fluid being produced. Most of the cases in natural gas production it is gas, but similarly most of the time the gas alone is not being produced. Gas is always associated with some amount of, it might be in a very small amount, some amount of liquid, that could be the oil, water, some amount of some small solid particles, those are also being produced along with the gas through this production string. That production string could be just tubing, casing or the annulus. The fluid in gas well are mainly gases, but as I mentioned, the condensate well will produce oil and gas. Even the gas well, which is gas well under the reservoir condition, when it is producing, the pressure drawdown is happening, and as we understand from our phase diagram class, the phase may get changed or the fluid may enter in the envelope of two-phase region where some liquid is also getting produced. And when this is happening, the liquid that is coming out of the gas phase under the local condition of temperature and pressure, that will get accumulated in some region in the valve bore and will create a problem, because this phenomena called the liquid loading and comes under special issues where certain actions should be taken to take out this valuable liquid from the valve bore region. Sometimes the production is not ceasing in the valve bore. WPR involves relationship between tubular size, valve head, bottom hole pressures, gas flow rate, and of course, the properties of the fluid. Our fluid is not ideal fluid, it is a mixture of hydrocarbon gases and non-hydrocarbon gases, and because of that the conditions, if conditions are changing like the local temperature and pressure, the fluid properties, specifically viscosity, compressibility factor, density, those are the function of temperature and pressure, will also change. We will see in today's class not only the properties, when the properties are changing, the equation those represent particular phenomena becomes complex, and solving those equation needs certain approximation, then only we can achieve the desired result. The desired result is how my flow rate through this valve bore is related to this big pressure drawdown that is spread over several thousand feet depth from PWF, means from the bottom of the valve bore to the head of the valve, and that relationship is called WPR. As mentioned, production can be achieved from the tubing, from the annulus or from the casing part, but experience shows producing through tubing is a better option because it prevents liquid loading. The superficial velocity of the gas and liquid, if liquid is present in the system, the relative superficial velocity decide the liquid accumulation is happening or not, or what is the liquid loading possibility in the system, and experience shows if it is happening through the tubing, the chances are less. Mathematical model are also valid for casing flow and casing tubing annulus flow. As mentioned, only difference will come in the mathematical equation which is derived for the tubing flow if the diameter of the tubing in that expression is replaced by the hydraulic diameter. By the definition, hydraulic diameter is 4 times cross sectional area divided by wetted perimeter. So, if we go by the definition of hydraulic diameter, we can write this HD, that is 4 times cross sectional areas. If the tube is slender, the cross sectional area the fluid is flowing is a pi d square by 4, and the wetted perimeter means the perimeter of this tube is pi d. So, if we do that for a slender tube, it comes out as the diameter or the internal diameter of the tube. So, in case of annular flow, the HD will be like the internal diameter of casing minus outer diameter of tubing. So, just replacing the diameter in the expression by the hydraulic diameter, we can use the same mathematical expression for flow through annulus. So, let us go ahead with this understanding of the basic WPR, why it is important and how to do it. We can set up the mathematical equation by considering the pipe could be either the horizontal, vertical or inclined. So, let us see, this is our tubing through which the flow is happening, and we are assuming the flow is happening from this direction to this direction, from 1 to 2, or I can say this is the place where the pressure is PWF, bottom part of the valve, and this could be PHF. This tube could be horizontal, vertical and inclined, but in case of the valve bore production, mostly it is vertical. We can adjust that thing with the help of angle theta, either we can use this angle or this angle, depend on the angle we are choosing, either the sine form or cos form will come into expression. We can say the length of the tubing, that is spread over several thousand feet, we can say the length is del L or just L, and the vertical height is del Z. So, we can establish the relationship, and that relationship says we are having del Z is equal to cos theta del L. So, now flow is happening from point 1 to 2 because of the pressure difference, and pressure difference is PWF is higher than or way higher than the PHF, and this pressure energy will push the fluid to travel from bottom part to top part of the valve bore. The diameter of this tube is internal diameter, we can say di, depend on the unit system it is mentioned, either it is mentioned capital Di or small di. In general, in US field unit system, if it is mentioned as small di, means the unit associated with this diameter is inches, and if it is capital Di, it is feet, or otherwise it is specified the symbol along with its unit. So, for this system, when the flow is happening vertically from point 1 to point 2, because of the pressure difference, we can set up the continuity equation or the momentum balance equation. Continuity equation simply says there is no accumulation of the mass is happening, whatever is entering at this point, let us say cross sectional area A1 and leaving at this cross sectional area 2 is same, there is no accumulation in the system, and when it is happening we can say Q1 is equal to Q2. So, the flow rate or volumetric flow rate or mass flow rate, we are assuming here the density is constant at 1 point and 2 point, that may not be correct, but what we are saying for the assumption the flow rate is same and A1 V1 is equal to A2 V2. Otherwise, it should be rho A1 V1 is equal to rho A2 V2. But from the continuity, we could understand there is no accumulation happening in the system, and we assume the density is not changing much. The cross sectional area of the tube is also constant or almost constant throughout the tubing path, then the velocity will also be constant, and that gives us the flexibility to assume the contribution of the kinetic energy in the momentum balance equation is negligible. So, when we talk about the momentum balance equation, momentum balance means the momentum getting in and out of the system, the difference between in and out will be balanced by the forces acting on the system. These forces could be kinetic energy, could be gravity, could be friction forces, could be shaft work done on the system or other type of the forces. Assumption we can make only gas is flowing. If we assume other than gas, liquid or solid compound or water is also being produced, the expression will be more complex, more difficult. So, let us start with a single gas phase flow system, and the flow through this tubing is governed by the first law of thermodynamics, that is the conservation of energy principle, and that by setting up the mechanical balance equation to a system, we can get the relationship between the parameters those are responsible for this conservation of energy for this flow that is happening through the tubing. If we do so, we can see, considering there is no change in the cross sectional area, the kinetic energy changes in the system can be ignored. Similarly, there is no external device installed across the system, so no shaft work is done on the system. It means shaft work is also negligible. So, the pressure energy in the system, this is pressure gradient, is balanced by the gravity and the frictional losses. Depend on the pipe roughness, the frictional losses will happen in the system and the gravity will play a major role. In fact, when the tube is vertical and the flow is happening because of the pressure gradient, as we see in our fluid mechanics class also, we can set a very simple mathematical equation. Depend on what is happening in the system, we can establish the relationship very easily in the terms of dependent and independent parameter. Similar we are doing here, but it is little bit complex, and the complexity is because our system is not ideal system, certain properties are not constant, they are the function of local conditions. So, let us see in the mechanical balance equation what we are having: the pressure, energy, gravity energy and friction losses are come up in the form of mechanical energy balance equation, and the summation of all these three is equal to 0. So, the pressure energy that is responsible for this flow is balanced by the gravity and frictional forces. Depend on the pressure gradient we are having, the flow will happen. In fact, in a vertical flow system, the gravity contributes around 75% and the frictional losses account around 25%. So, the gravity is a dominating mechanism or dominating force or dominating part of the energy change that's actually govern the flow through a vertical tubing. We will discuss this in the next slide, how the parameters appearing in this expression can be replaced to make this equation solvable. Because you see here the pressure term, the gravity is appearing, the natural gas is a real gas, gravity may not be constant. In most of the cases, as we consider natural gas is a compressible fluid, of course, density is not constant in that case, and the F, which is a frictional force factor or called as a friction factor, F that comes out by the definition of stress by rho v square by 2. We can get if we know the tau, rho and v, or we can convert this expression into other form in the form of Reynolds number, and can use some charts from our fluid mechanics class. We understand a Moody's chart is available that's relate how the friction factor or the Moody's friction factor should be calculated when we know the flow through a pipe is happening and under what condition that flow is happening. It is happening under the laminar condition or in a turbulent condition or in between like in a transient condition. We will see that in the next slide. Important is this F that is also a function of Reynolds number. Reynolds number is a function of Q, the volumetric flow rate that we will also see in the next slide, and the Q is a function of temperature and pressure. So, this F is also going to create a problem. It is not easy to put some value and take it out. Similarly, the velocity V is equal to Q by A, and this Q again depend on the local condition, temperature and pressure. So, we will see how we can replace the parameters those are making this equation difficult to solve, how we can replace those parameters in some other term or in some familiar term those we know or we understand how to calculate from the understanding of fluid properties. So, we say the density rho is equal to 29 gamma z p y z r t. This we understand from our properties of natural gas class, how to establish this relationship. Here gamma z is equal to molecular weight or apparent molecular weight of the fluid or the gas divided by molecular weight of air. So, indirectly the gamma z is accounting the type of the fluid or the gas is being produced from a gas well, and in other terms what are the composition of that gas, how much percent of particular dominating hydrocarbon and non-hydrocarbon compounds can be represented in the form of gamma g. Gamma g accounts for the compositional variation. From a particular well, we may be producing just a constant composition until unless some extreme conditions are happening, like pressure is declining, some liquid accumulation is happening or some phase separation is happening. That separate, if the compositions of the gas are known, we can calculate molecular weight. Knowing the molecular weight, we can calculate gamma g. Putting gamma z here, we can calculate rho. But again, see here, rho is also depend on Z. Z is compressibility factor, and that compressibility factor is also a dependent term that depends on temperature and pressure. That also we had seen in our properties of natural gas class, how to use some empirical correlations or big chart to calculate the compressibility. We can use Brill and Bax method to calculate the compressibility. That gives us little bit easiness in creating a Excel sheet where putting the data we can get the compressibility, but compressibility factor is required. Similarly, here for the velocity, as mentioned last slide, we can write Q by A. A is cross sectional area pi d square by 4, or we can write internal diameter of tube. Q is a flow rate at a particular temperature and pressure. So, we can use the relationship that says at a particular condition Qp by ZRT at one condition for a real gas is equal to Qp by ZRT at second condition, and the second condition we can assume as a standard condition, and at that standard condition we know what is the pressure value, what is the temperature value. We can cancel out this R, and the Q value that will be denoted by now QSC, because this Q is estimated assuming the estimation of the flow rate, or the Q value is done at standard condition. The Z value, even the gas is real gas, but we consider the Z value at standard temperature pressure condition as 1. So, the Z2 will become 1. By doing this, we know how to put those value and get the expression for velocity. Putting area, putting this relationship of the real gas, we got this expression. Here PSC and TSC are standard pressure and temperature. We know in a field unit system the P is 14.7 PSIA and TSC is 520 degree Rankine. R value at the field unit system is 10.73. If we put this numerical value, we can get the value of velocity in some numerical term also. Now, Reynolds number, the parameter that characterize the type of the flow is happening or required to calculate the friction factor. So, the Reynolds number is rho v d by mu. Now, if we put rho value, velocity value in that expression, and this is di, internal diameter of the pipe, and the viscosity of the fluid that is being flowed from the tube. If we put everything, we will see the expression we are getting like this. Here the question comes, at what condition the viscosity should be calculated, because again the viscosity is a function of temperature and pressure. So, the viscosity of the fluid that is flowing through a tube can be calculated under certain average temperature and pressure condition, and that is why the bar on the mu is appearing in the expression. It means the mu is calculated at average condition. The average could be chosen like the well head temperature pressure and bottom hole temperature pressure and the average, or by some other mean the average could be applied to calculate the viscosity of the fluid. Otherwise, it is very difficult because viscosity will also change at point to point. When we put the standard condition, standard temperature and pressure condition and get the expression for the Reynolds number, it appears very simple expression like the rho v d by mu. It says under the US field unit system, the Reynolds number is equal to 20.09 gamma z QSC, means Q estimated at standard condition, divided by d, diameter of the pipe, and mu, the viscosity of the gas that is flowing through this tube. So, now let us see our balance equation that we had in the last slide, that says the pressure term here. Now, we know we can replace this rho, we see here the F, we will see in the next slide, but now how to replace this V, we know that thing, and the F could result in a numerical value. Again, numerical value depends on the Reynolds number and the roughness of the pipe. If roughness of the pipe is known, Reynolds number at which the fluid is flowing through a tube or a pipeline is known, we can calculate using the Moody's chart. So, we can put the values in this expression and can derive the mathematical expression that is much familiar compared to this one. We will do in the next slide. Here important part is the F that is appearing here, is it a Moody friction factor or a Fanning friction factor? There is a relationship between Moody and Fanning. Moody's is 4 times of the Fanning friction factor. Whenever it is not mentioned, it is a Moody friction factor, until unless it is specified, it is a Fanning friction factor. In the expression or in the chart which we are going to use, the relationship of Moody and friction factor should be adjusted to have the accurate understanding or the value of the friction factor that is going to be used in this mathematical expression. So, let us see how to see this expression when we put the value other than this F, that we will see how to calculate it. The equation will appear like this. So, this is still the pressure term, we just replace the density and here we had replaced the velocity. So, the first term, the pressure term, now depend on P Z R T. Similarly, second term is also depend on Z T by P, and if we can establish the relationship, this equation can be solved. Otherwise, this equation cannot be solved in the current form. We have to make certain assumptions in terms of how to calculate the compressibility factor, how to make the assumptions the compressibility factor can be integrated when we are going to integrate this equation. Similarly, for the pressure and temperature, we will see later on. Let us understand first how to estimate friction factor. So, this chart shows about the friction factor versus Reynolds number, and this chart is for the Moody's friction factor. I already mentioned Moody's and Fanning friction factor are different. They are having a relationship of Moody's friction factor is equal to 4 times of the Fanning friction factor. Here you will see the Moody's friction factor. Similarly, Fanning will also be a function of Reynolds number and epsilon by d, this is called the effective roughness of the pipe. This is the value epsilon that should be provided by the vendor who is supplying the pipeline, or if it is not given, there are several literatures those allow us to calculate the effective roughness of the pipe. Important is the Reynolds number. The Reynolds numbers, if the Reynolds number is known and the roughness of the pipe is known, we can read this chart and can calculate the friction factor value. Depend on in which region the flow is happening. If it is happening in the laminar region, the expression is simply 64 by Reynolds number. Here it is Moody friction factor. You will see other chart, when it is Fanning friction factor, this will be having 16 by NRE. But in the Moody friction factor, it is 64 by NRE. So, let us talk about the Moody friction factor only now. So, when the flow is in a laminar region, it is having a relationship like the Reynolds number, the friction factor is declining, and it is not a function of roughness of the pipe. The roughness of the pipe plays a major role when the flow is in turbulent region or in a transient region, when the gas is flowing with a significant high velocity, and that is the case in the case of natural gas. Because of significant pressure difference, the gas is flowing under the turbulent condition, and in that case epsilon by d needs to be known before we can read this chart, because you can see here there are several lines, those are inclined and then becoming flat. Flat means of certain Reynolds number, the value is not depending on the Reynolds number, it just depends on the roughness of the pipe. In the transient region, the region becomes little lesser, and means the effect of roughness of the pipe just concentrated in this region only, and we can calculate the effectiveness factor if we know the value of Reynolds number. And we know Reynolds number depends on the Q or gamma g. Gamma g can be estimated if we know the composition of the gas, but the flow rate that depends on temperature and pressure. And if the temperature and pressure are changing, flow rate will change, and when flow rate is changing, Reynolds number will change. When Reynolds number is changing, the F value which is used using this chart or any other correlation will also get changed. So, important is putting some iteration method to estimate the value of Reynolds number, that is satisfying the condition of the flow rate at which the fluid is being produced. Another thing is NRE in the SI unit system or in the field unit system. If it is represented in SI unit system, the rho v d by mu kind of the expression will be there. We can adjust in the other terms, and when it is in US field unit system, because of the unit chosen to represent different parameters, those are appearing in the expression, some numerical coefficient may appear, and that similar thing is appearing here because of the adjustment of the parameter. The diameter, sometimes it is given in inch, sometimes in the feet. If we are not converting using di small, that means the diameter is in inch, the numerical coefficient that is appearing will get changed. So, we should be careful when we are dealing with a different unit system. The expression may end up with some numerical coefficient because of the unit chosen to express one of the parameter that is appearing in the expression. So, let us go ahead. With this understanding, we want to know the Reynolds number. If Reynolds number is known, we can calculate friction factor. Of course, the effectiveness roughness of the pipe or the effective roughness of the pipe is also required. This is not only the way we can calculate the pipe roughness, or this is not only the way with which we can calculate the friction factor. There are several correlations depend on this chart or on other understanding reported in the literature that says how to calculate the value of F. As already mentioned, the gas mostly flowing in this valve is mostly follow the turbulent flow, and for fully turbulent flow several expressions given in the terms of diameter of the pipe, in terms of the effective roughness of the pipe, or in terms of Reynolds number, or the combination of all three. So, here Katz and Lee, they had given the expression for the fully turbulent flow condition, and the expression is divided based on the diameter. That's they said if the diameter of the tube which is used to produce the gas is lesser than 4.277, lesser than or equal, the expression can be F is equal to 0.01750 divided by diameter to the power 0.224. And if the diameter is greater than 4.277, the expression will be different, and that says the numerator part as well as in the denominator the power of diameter will also get changed. So, depend on the diameter, Katz and Lee had given this expression. Goa used Nikodsev friction factor correlation for fully turbulent flow in rough pipe, and that they had considered this is not depending on alone the diameter of the pipe, but on the effective roughness that is described by epsilon by di, and the epsilon value is something that is specific to a pipe that is used to produce the flow. So, either it can be calculated or should be supplied by the vendor, but this relationship simply says the F can be calculated just by F by di relationship. We do not need the Reynolds number, but there are several correlations are reported in literature, and they are developed based on the understanding of the flow through pipeline, how the pipeline roughness, the diameter and the flow regime, that is laminar, transient and turbulent occurring in the system, the correlation can be used. All are good enough under certain conditions, especially the Suomi and Chen equation is considered better than this Colebrook equation or Chen's equation or some other. All are good, but depend on which one is chosen, what is the information is available and what accuracy the results are required. As mentioned, Katz and Lee just they mention it depends on diameter only. Nikodsev relationship, it depends on epsilon by di only, and similarly if we write about the Suomi and Chen equation, that says how the friction factor is related to the other parameter like 1 by root f is equal to 1.14 minus 2 log epsilon by d di, of course it is an internal diameter, plus 21.25 divided by Reynolds number to the power 0.9. So, Swami and Jain consider Reynolds number also in the estimation of friction factor, and that is knowing the expression for friction factor or the correlation proposed in the literature, we can calculate the friction factor value. And once we know the friction factor value, now in this expression we know how to replace rho, how to replace f, how to replace velocity. And when we did arrangement of this equation replacing these terms, we could get this expression. This expression simply says here this is pressure and this is length. So, the entire tube length in the inclined condition, because the cos theta is appearing here in the inclined position, the expression says how pressure drop is related to length for the entire length of the bell bore. If we can solve this equation, we can get that relationship. But see here the expression is still having the complexity. It cannot be solved so easily because the Z is appearing here, the compressibility, similarly the temperature, similarly the pressure. We know the flow through this bell bore is happening because of the pressure. For example, we are having this vertical tubing and the flow is happening. So, of course, the PWF is higher than PHF, and at intermediate position the pressure should be different or between PWF and PHF. Similar, the temperature is also different here, let us say TWF and THF, temperature is also different, they cannot be taken constant. And when temperature and pressure cannot be assumed constant in an actual case, then how compressibility can be taken constant. So, after adjusting the parameter in the mechanical balance equation, we could establish the relationship for a single gas flow system. This is an ordinary differential equation which is governing only single gas flow through the tubing. It is equally applicable for the casing and annulus, as already discussed. We just need to replace the diameter by the hydraulic diameter. This equation is still very complex because our fluid is a real fluid. It is complex in the nature, its properties changes when we are going to deal with this fluid at different temperature and different pressure condition. The fluid is compressible, thus the density and viscosity vary along this tubing line because the temperature and pressure are also changing. Some assumption can be made like temperature is changing linearly with respect to the length. So, as we are going down from the surface, length is increasing, temperature is also increasing, that we can approximate it is happening linearly. But compressibility, that is a function of temperature and pressure, needs to be calculated locally, and that is put the condition on solving this equation, and this equation cannot be solved as an ordinary differential equation. This is the difference between the ordinary differential equation we establish when we are solving for the ideal gas, but in this case we are getting a complex system. So, certain approximations are required to solve this equation. There are several approximations have been reported in the literature to solve this equation, but two of them are widely used in the gas industry. One of them is the average temperature and compressibility factor method, and the second is Callendar and Smith method. We will go through one by one about both the method. So, the next method, the average temperature and compressibility method, that is assume the calculation of temperature, those are appearing in that equation. Previous equation we had seen temperature was inside, pressure was inside, and the compressibility was inside. So, after assuming like any mean, we can calculate the value of compressibility, temperature and F constant value. We can assume the entire length temperature, we can just average out by choosing wellhead temperature and the bottom hole temperature, the average value. Similarly, can be done for compressibility also, and for a local segment in the tubing length, if there are other ways available, we can calculate the average value of the compressibility and temperature. and when we can do that thing, we can take those term out of this derivative term, and this equation will take this shape. And in this equation, if we also assume f is constant, then you see we can take this is entire term as a constant, because we know the constant value of compressibility. R value is a numerical value, temperature value will be numerical value, and if we know the composition of our gas, we know the gamma z. So, we can write this as a constant, and this is A1. Similarly, this is also constant value A2. If we know the inclination, if it is horizontal, vertical, or at a particular angle, we know this is going to be a constant, and this is A2. And here also, other than P square, we can say everything after putting the standard pressure, temperature, pi value, compressibility, factor value, average temperature value, this is going to be A3. So, if I write this equation in a simplified form, here in this equation we had assumed all these are having constant value. So, if I arrange this equation, this will take shape like dP by P plus A2 plus A3 by P square dl is equal to 0. Now, we can apply the separation of variable concept to solve this equation. Let us further simplify this equation, and if I do so, what I am going to get is A1 dP divided by P A2 plus A3 by P square is equal to minus dl. Before we are going to integrate it, let us further simplify this. We can take this A1 out here, and we will get this equation in this form: P A2 by A1 plus A3 by A1 1 by P square, and on the right hand side we are having minus dl. So, we can lump the parameter again, and A2 by A1 we can write as a B1, and A3 by A1 is B2. So, the equation will take the form of dP by P B1 plus B2 by P, and on the right hand side we are still having the minus dl. Now, the B1 and B2 we had lumped the parameter, the numerical coefficient, and we can write what will be the form of B1 and B2. So, if we write this, will be having some numerical coefficient x, gamma z cos theta by average compressibility and average temperature. Similarly, the B2 will be having some numerical coefficient f gamma z q s c square z bar t bar, and this numerical coefficient, that x, and here we can write x prime, depend on the unit system has been chosen. So, if we take field unit system, the B1 value will be 0.01875 in the US field unit system, and the B2 value will be 5.057 10 to the power minus 17 again in US field unit system. And if we convert that entire expression to SI unit system, the value will be 0.0317475, and for B2 in SI unit system it will be 4.658 10 to the power minus 14. Depend again on the unit system chosen. Even for individual parameter, if we are changing the value of measurement, for example, the diameter is changing from feet to inch, the numerical coefficient will get change. We understand in US field unit system, the standard value for pressure is 14.7 psia. We can put that value. Temperature is 520 degree Rankine. Diameter, again here it is put in feet, and the QSC is in SCF per day. While in SI unit system, the pressure value will be measured in kilopascal, and that is equal to 101.4 for the standard condition, and temperature is 289 Kelvin, diameter is measured in meter, and standard flow rate is measured in standard meter cube per day. So, depend again the unit system we are choosing, the constant value V1, V2 will get changed. We do not need to worry about those parameter at this moment. When we are adjusting the equation, finally we can care about it. Now, our equation is here that we should care at how to integrate this equation from P1 0.1 to P2, or from length L to 0 we can integrate this equation. For further simplification, what we can do? We can take this term out like B1. So, we left with P1 by P2 dP upon. So, if we take B1 out, we will be having here P dP P square plus B2 upon B1, and we can consider further this B2 by B1 is like A, another parameter just to lump B2 by B1, and on the right hand side by integrating this we got the value L. So, on the left hand side further we are having 1 by B1, integrating it from P1 to P2 we got P dP upon A plus P square. Right hand side we are having L. Now, to further solve this equation, we can assume A plus P square is equal to some parameter, some local parameter we can say is x, and if we differentiate this we will get 2P dP is equal to dx. Using this we can convert this equation in the form of x, and when we are doing that we will get 1 by 2B1 dx upon x, integrating it from x1 to x2, and right hand side we are having L. The integration will give us 1 by 2B1 ln x2 by x1 is equal to L. By adjusting this equation, we can get ln x2 upon x1 is equal to 2B1 L. Further, x2 upon x1, that is equal to, if we write in terms of the pressure, is A plus P2 square, A plus P1 square. Further, A is equal to we know is B2 by B1. So, we can write B2 by B1 plus P2 square divided by B2 upon B1 plus P1 square. Now, we integrated L from L to 0. It means the pressure range should be at L, pressure is PWF, and here it is PHF. So, the P1 will become PWF and P2 will become PHF. After adjusting this equation, what we are going to get is equation like this. You can do the adjustment putting V1, V2 value and everything. If you adjust, we will get this equation which says how Q flow rate is related to PWF, PHF, diameter of the pipe, and the fluid properties like the compressibility as well as viscosity. Viscosity is related in the form of, because to calculate the Reynolds number we need the viscosity, and of the Reynolds number is required to calculate F. So, the F which is appearing here is in the form of implicitly accounting for the viscosity, and the S here which is appearing here, this is similar what we got in terms of B1, B2 parameter, this is equivalent to 2 B1L, and after putting the value of B2 here, we are going to get the same expression here. We can understand how this equation is going to help us to establish this relationship. Now, we could solve the equation which was not solvable with the assumption of constant temperature and constant compressibility. The equation could be solved. The equation had given us the relationship between the flow rate and the other parameter, those are responsible for this flow, like PHF, PWF, diameter, compressibility and viscosity. Again, the numerical part or the numerical coefficient appear in this equation depends on the unit system chosen to represent particular parameter. I am emphasizing again, the DI, it is sometimes given in inch form, sometimes it is considered in the feet unit, and the adjustments should be made accordingly. The SI unit system, this should be SI unit system, where pressure, temperature and R value can put here, and in field unit system we are having different value, like pressure is measured in PSIA, temperature in degree ranking, and R is having feet cube PSIA per LB mole degree ranking unit. If we put this in this equation, we will get final the numerical coefficient that is appearing in this equation, and this is again in the US field unit system, where D is considered in inch. The average compressibility factor is a function of pressure itself. So, the problem is not solved so simply. We could solve that equation, the equation which was looking like an ordinary differential equation, but not having any analytical solution. We could solve that equation considering the constant temperature and constant compressibility, apply the separation of variable concept and got the solution. But here the problem with respect to compressibility is still there. That says compressibility is a function of pressure. That is numerical technique like a Newton-Raphson method or other technique is required that can help us to perform the iteration and find out what should be the value of PWF or any parameter that is missing here should be. We will understand this with the help of an example. So, the example for this problem is chosen from the book that says develop the pressure profile along the tubing length, and some values related to this problem are given to us. So, let us say this is the well bore which is spread over the length from 0 to L, and the length is given like it is deeper up to 8000 feet from where this is producing the fluid, and the fluid which is produced is having the specific gravity as 0.7, and the production rate QSC is 2 mmSCF. 2 mmSCF is 2 million standard cubic feet, and the temperature at the top is given, that is 150 F, and at the bottom this is 200 F. The pressure is also given at wellhead condition, and that wellhead condition says the pressure is set at 600 PSIA to have this production QSC at 2 mmSCF per day. Other things are given, the diameter is given as 2 inch, and the roughness of the pipe is also given, epsilon by d is 0.0006. If the value is not given epsilon d, this is the value that should be assumed as an standard value. Now, we were asked pressure profile along the tubing length. So, as we are going from top to bottom, what is the pressure at each section which we are going to consider, or ultimately what will be the pressure at the bottom of this well bore. PWF is not given to us, this is PHF is given, THF is given, TWF is given. So, if we look our problem or our mathematical expression, where we say we have the expression with the help of average temperature and average compressibility method, where PWF is related to PHF and other parameter. Important point comes, we need to know the value of F. We can go with any formula given in the literature, but what we can do, we can choose one of the accepted and simplest form that does not need any value of Reynolds number. Even if it is required, we can calculate because we know the Q value in this problem. So, let us use the value of f from the expression given by Nikodze, and that says f is equal to 1 upon 1.74 minus 2 log epsilon by d, and this is whole square. See, in this expression there is no Reynolds number appearing, just only the roughness of the pipe and internal diameter of the pipe, or other way effective roughness of the pipe is considered. We know this value, we can calculate very straight the value of f, that will come as 0.017397. You can perform that calculation and you will see the value is coming like this. Now, we know the f value, we know temperature at the top and bottom, we can calculate the average temperature. Now, how to solve this problem? How to know how the pressure is changing as we are going downside from surface to bellbore's bottom point. For that, we can look at the expression and can say at any particular length from the surface, any particular length PWF can be calculated. We need to know the compressibility, other things are known, and that is where we can play the trial and error or the iteration procedure, because compressibility depends on pressure itself. So, at a particular location what is the pressure, then only we can calculate the average pressure, and that average pressure the compressibility can be calculated. So, for that purpose what we can do, we can design a spreadsheet, and that spreadsheet says your length, this is length or this is length data from 0 to L, that is 8000, is divided in n number of equal parts, and we can choose 10 or we may go up to 100 or any number. 10 is something that will allow us to do fast calculation. We can write a mathematical program to solve this kind of the problem, because every time we need to do the iteration, and for that purpose there should be either in Excel or in MATLAB or somewhere the program that is performing the Newton-Raphson method or trial and error iteration procedure. So, let us say first thing we divided this entire length from 0 to 8000 in 10 segment, and now we assume the temperature changes linearly with length. So, the temperature data can be obtained very easily. This temperature is in degree ranking. So, at the surface the temperature is 610 and at the bottom it is 660. The next is pressure. Here I had shown the entire result, but we know only this value 600 psi as a PHF at the surface, or at the wellhead the pressure is 600. Now, at this pressure, at this temperature, we can consider these are the average value, we can calculate this compressibility factor. Now, how to calculate compressibility factor? We have to go back in our natural gas properties class, where we understood the methods how to calculate the compressibility factor. One of the method is Brill and Beggs. We can use that method considering the critical temperature and critical pressure of the system, that can be calculated because we know the gamma z of our system, and based on that we can calculate the Z. Now, this Z should be calculated at average conditions. So, what we will do at the next level, we will assume some value of P2 and calculate the compressibility factor, and we will see the compressibility factor calculated by performing the iteration for this PSI should satisfy the function value, and if it is satisfying we will get PWF at that length. And similarly, we can go down and at the end we are going to get the value of PWF at the bottom of the well. So, now once we could do this calculation, we got the length, we got temperature, we got pressure. We can plot pressure profile as we are going down from this 0 length to L. We know at the 0 surface we are having some pressure. So, let us say this is depth and this is pressure range in PSIA and this is in feet. So, we know the total length is 8000. At surface, when the length is 0, we are having a pressure that is 600, and after performing the calculation we came to know at the bottom the pressure is 922, and intermediate length, at intermediate length we can put the value of pressure and we can get the profile that is saying how the pressure is changing from PHF to PWF, and that is the way we can solve the problem for any length if the PHF and Q and other parameters are given to us. Let us see another example where we will understand in a better way how we can choose this particular equation to calculate the unknown parameter or the missing parameter that is not available. This will also help us in designing the system. For example, in the second case, when the diameter is chosen to a system when Q is known, PWF is known, and in the first case when PWF was asked what should be the PWF, when Q is given, we can do the same thing. We can divide this length in n number of part, perform the same iteration procedure as we did in the last slide, and we can calculate the PWF. What in the other case, when it is said PWF is given, Q is given, diameter needs to be calculated. Again the same set of the equation can be used, where PWF is known, not the diameter. We can perform the iteration, and the iteration is required. It cannot be solved straight. Iteration is required if we are going to use how to calculate the F. If F value is constant, the friction factor is constant, we do not need to perform the iteration, but that is not the case. We are having F that depends on the diameter or internal diameter of the tube. So, when we are going to calculate the internal diameter of tube, we have to perform the iteration with respect to F to get the optimum solution or the size of the diameter, internal diameter of the tube that is going to satisfy at that PWF, at that PHF, this flow rate can be achieved. And this PWF case, in the first case, we need to perform the iteration because we need to calculate the compressibility F, we need to perform the iteration because we need to calculate F. In case of third, when PHF, PWF are given and we are supposed to calculate Q, we can use the same equation, we can perform the iteration again, and the iterations are required because we know the Reynolds number value or the F value. If we are going to use the complex formula where we want the F is a function of Reynolds number, and to calculate the Reynolds number value we need the Q value. That is why with respect to Q we need to perform the iteration. If not, then we can solve it in a much easier way. And if we are doing this exercise by using this equation, we know several parameters, those are known to us. Like in the first case, we are having PWF should be calculated, others are given to us, like average compressibility can be calculated by iteration procedure, otherwise T average, diameter of the tube, PHF given to us. And in that case, when we perform, this is left an exercise, we will get the PWF value as 1440. While in other case, when we are doing with respect to diameter, the answer will be around 4-inch tube is required to achieve this flow rate when PWF, whatever the PWF is given, we had chosen that. So, this PWF is used here. And in case of when Q is supposed to be calculated, when the flow is happening between this pressure gradient, we are going to get the value of Q as 15.8 mm SCF per day. We can perform the iteration, and you can solve this equation considering the parameter given in the previous case. Only the missing parameter or the parameter which is asked can be put for the solution purpose, and the answer I had given. This is 4 inches diameter, the flow rate will be 15.8, and for the first case the PWF will be around 1440 PSIA. That is where the average temperature and compressibility method can help us solving that equation. Even though it is an approximation, still it works and widely used in the gas industry. The second method that is also used in industry very frequently for such kind of the calculation is Kullender and Smith method. So, the Valbor performance relationship as we know is an ordinary differential equation, cannot be solved just by doing the simple ODE procedure, because the compressibility and other factor depends on local condition or temperature pressure that is changing. Similar procedure as we understand for the previous method, it could not be solved, but making certain approximation, by making certain approximation we could solve it. Kullender and Smith also made an approximation, and that approximation says why we cannot arrange this equation in the form of this, where we are integrating from PHF to PWF, and the equation is going to take this shape. This is just adjusting everything related to pressure on one side and length related to on the other side. We can do that arrangement, and when we do so, the numerical coefficient appearing here depends on the unit system has been chosen. This is for the US field unit system, where QSC is taken in SCF per day, and the numerical coefficient appearing because we had put the value for the standard temperature, standard pressure and other parameter. Now, in this equation you will see P, Z, T, they are the function of local condition, the compressibility at a local condition, temperature and pressure will also change, and similarly F, if F is a function of not only the roughness, but also the Reynolds number, it cannot be considered as constant. But altogether, by arranging this way, we could get integral form of this equation that says, if you consider this entire thing as I integrand, and you can put PHF to PWF, that will be equal to right hand side. After applying the trapezoidal rule, we can approximate this entire tubing length in two parts, and at the midpoint, let us say this is midpoint, this is head point, this is bottom point. Here the pressure is PHF or any property is PHF, here it is PMF, and here it is PWF. So, this is if you integrate this previous integrand at this PHF, we will get IHF. If you integrate at midpoint, we will get IMF, and similarly at the bottom it will be IWF. And this can be done with the help of the trapezoidal rule, that simply says if you are integrating any function from a to b dx, that will be b minus a, the difference in the range, function value of a, function value at b divided by 2. So, similar thing has been done. If you see here, the entire section is divided in two parts, and it is assumed the upper part and lower part are having the same value. We will see it next. Let us see first, after applying the trapezoidal rule, we got this is the difference in the limit a minus b kind of the things. This is the function value at midpoint and top point divided by 2, similar for the bottom part, it can be done. So, we can divide in two parts, perform the integration, and that is equal to right hand side. The right hand side is going same. Here it is assumed like the first part and second part, they are equal in terms of the value we are obtaining after performing the numerical integration, and that assumption says this is like this, and this is just half of the right hand side. Similarly, the other term here, that is half of the other side. If we sum both of them, we are going to get the same thing. So, assuming this first and second term in the right hand side of equation, each represent half of the integration, that is give us the flexibility to have to algebraic equation, those allow us to perform further calculation to get the value of PMF, the pressure value at the middle point. We already know pressure value at head, and similarly we can calculate the value at bottom point. But how to get this? Still there is a problem, because when we are adjusting those previous equation in the form of PMF, we are getting PHF plus 18.75 gamma ZL and the summation of both the integrand. Here this says the IMF, when we are calculating IMF, that is a function of the pressure itself. We need to know the pressure here PMF, then only we can perform the integration at that point. That is why again the Newton-Raphson or any iteration procedure is required, that allow us to calculate the pressure at that condition which satisfy the integration condition. And once we know PMF, we can put in this equation and we can get PWF. This IWF is appearing here. IWF is a function of PWF. We have to perform iteration again for this condition also. But by performing the Kullender and Smith method, we can divide the section in two parts and get the solution. Let us understand the similar problem what we solved in the case of the average temperature and average pressure method. We can say the same thing where the length is spread from 0 to 8000. We know the pressure here PHF, that is 600, the temperature we know here is 150 R, or other way 610 Rankine THF, and here the pressure is supposed to be calculated while the temperature is given as here is 660 R. Now, the problem is same, we can divide this in two parts. So, this is 0 to 4000 and here it is 4000 to 8000. Now, what we know, let us say we know the length, we can divide this length 0, 4000, 8000. We understand the linear approximation with respect to temperature, and when we assume that linear approximation, we know here it is 610, here it is 660, we can write the value of temperature at the midpoint also. That will be the average of this thing. So, if I take the average, this will be around 635. Now, it comes to pressure, how the pressure is changing. We know to know the pressure, we have to know the integration or integrand function, and that integrand function depend on P by ZT. Now, we have to calculate P, because to calculate this function we have to know the value of P. Similarly, to calculate this function we need to know the Z, and we can do the similar what we did the iteration procedure for the average temperature and average method to know what will be the value of pressure and temperature. At the initial condition, we know the pressure is 600, we can write that value here, and next considering this and this value for the pressure and temperature, we can calculate the compressibility at that point, that will come out as 0.9297. We can calculate now P by ZT at that point 1.05803, and integration at that point this will be 312 point something. Now, for the next, at this length we do not know what should be the value of that. We can perform the iteration with respect to Z to get the value of pressure here, that will come out as 764, and the value of compressibility at that pressure will be 0.9332, and accordingly we can calculate P y ZT and integrand. And further, at the length of this we can calculate this value 923 will come after performing the iteration, and at that condition we will be having 0.9213, we can get P, ZT and this. And if we solve those algebraic equation, because now we know these values IMF and IWF, we will see the value of PWF 923 and PMF is appearing the same. So, now both the methods have been discussed. There are not only these two methods, there are several other methods. Those also allow us to calculate the pressure profile when the flow is happening through this valve bore. Several methods are just like the Kullender-Smith method. They suggest how to divide this entire length in n number of parts. Not necessary those equal interval is needed for those small segments. We can calculate, perform the trial and error or iteration procedure, the pressure at each segment, as we did for the temperature and compressibility method and as we did for this Kullender and Smith method. Those we are not going to discuss in detail, but there are some methods available. I think Kullender and Smith and the average temperature and the average compressibility methods are good enough to solve our purpose. If we go further, we can get with this Colander-Smith also the same temperature, same pressure profile we can obtain with respect to L. We know at this point what is the pressure 600, and when we reach up to 8000 feet, we are having almost like the same. Here we got 923 value, and at the midpoint we got the value at 764. We can draw the profile. Once we could establish this relationship, we know this balance equation is functioning well, it is representing what is happening in the Balboa condition. Another advantage of this is drawing the WPR curve. So, now we know at different PHF or different PWF how Q is changing, and knowing this curve relationship will help us to understand or the designing of WPR system. We will discuss this WPR curve later on when we will be discussing about the nodal curve analysis. So, with this, what we did so far, we understood how to set up the mathematical equation for WPR, just considering it is happening under steady state condition. There is only one single phase gas is flowing through this well, but that is not the situation. If we see even dry gas well also produces a small amount of the liquid, that could be the water or could be oil or the condensate. In the surface we are not seeing any liquid, but during the production there might be some zones where the liquid is coming out of the gas phase and getting accumulated. So, when we are having the two phase system like the gas liquid flow system, we may have a very complex system. It is not just two phase flow system where we can understand how the flow will be happening. It depends on the superficial velocity of the gas phase and liquid phase. What is the critical velocity? Is the gas is having enough energy or velocity to carry the liquid accumulating in the tube to the surface, or it is just getting accumulated in the system, and depend on the relative superficial velocity or the flow regime in the system, we can get different type of the two phase system, and each phenomena that is happening or shown here is having its unique characteristic to define the problem. So, for example, in the case when two phase is existing in the system, we can have a bubble flow. It means continuous liquid phase with dispersed bubble of gas. So, this kind of the flow is happening in a system. If we go further, large gas bubbles are formed and we are going to get the sludge flow. There might be the possibility of the churn flow where the bubbles start to coalesce and up and down motion of the liquid is happening, and the annular flow where gas becomes the continuous phase and droplet in the gas phase are formed, and we are seeing the flow is happening in this manner. That again depend on the relative velocity of the gas and liquid. In case of the gas reservoir, the gas should have enough energy to get flow, otherwise the production may get ceased. This is not only the possibility, there might be possibility even within a single Balboa system, we are getting a different zone where the bubbly flow, sludge flow, annular flow, dispersed flow, or just vapor on the top and the liquid at the bottom is happening. And for that there are some complex way, we are not going to discuss those in detail. Of course, depend on the inclination of the tubing. In most of the well reservoir problems, the well is always vertical with theta angle is 0. In problem we discuss, we consider just the vertical well. If the flow is happening in the inclined flow, the situation will be different. The flow regimes those are appearing will also be different. And when we are having the horizontal flow, the flow regime will be completely different, or the characteristic by which the flow regimes are defined will be different. Some of this part we will be discussing when we will be dealing with transportation of natural gas through horizontal pipeline or through inclination pipeline. But important point here is the flow happening in the tube depend on relative superficial velocity of gas and liquid. the flow regime or the slippage happening between the gas and liquid characterize the system, but we are keeping this as separate, not considering in the syllabus of natural gas engineering. There are more complex situation may happen in a system where not only the gas and liquid, but there might be a possibility that all four phases are present in the system. Even they might be in a small quantity, but if they are present, they are going to affect the system. The simple equation which we discuss is not going to help us even when we are going to two phase, and the question comes when we are going to four phases, how to define the system by the mathematical expression. So, Goa, Swan and Galambor in 2004, they had developed the expression considering all four phases are present in the system. Those four phases are oil, gas, water and some solid particle. Those may be the coal particles or maybe just the sand particles, and they had derived very complex expression considering all four phases, and in this case the situation becomes more complex. So, we also not going to discuss, but yes, there are model exists in the literature, those allow us to understand what happening in the two phase system, in three phase system or in four phase system. Certain assumptions have been taken to derive those equations. For example, this four phase model assume the gas phase as a ideal gas, and when we are considering this four phase model, reducing it to just a single phase model considering only gas is flowing, under that condition we see there is a difference in the result that we can get from the other method and from this method, and the primary reason is the assumption made to generate this kind of the expression for multi-phase flow system, where it is assumed the gas phase is a ideal gas phase. With this, I would like to end WPR part. Let us summarize what we did so far in terms of the petroleum production system. We could establish the IPR relationship, and in gas reservoir diluviality concept, we could see how Q, the flow rate in the porous media, can be related to some other parameter. Now, we had developed in today's lecture the TPR or WPR relationship, and in the next lecture we are going to understand this part where a device called choke is installed, and we will be having the understanding of choke performance and its mathematical expression. Choke is a device that is installed at wellhead or downhole to cause a restriction to flow of fluid, thus control gas production rate. So, restriction device is installed that allow us to make the restriction on the production, and that is installed most of the time on the wellhead and some of the time in a different form like SSSV, subsurface safety valve, in the wellbore or at the bottom of the wellbore. With this, I would like to end my today's lecture. Thank you very much. We will meet in the next lecture. Thank you.